Hello, this is Dr. Hassan Abdullah with the course Complexity and Analysis of Algorithms. So, the topic which we are covering is the last topic for the complexity analysis. And of course, we have more wonderful topics to cover. This topic is the advanced complexity analysis, but this is not advanced algorithms, which is the last topic of this course. So, the supplemental website is easymcq.com/goget. And we go ahead with the course contents. So, this is the course contents, and we are covering this topic over here. So very briefly about the supplemental website, which is basically a learning management system. So the address is here in front of you. So this has some wonderful features. You can customize the course as per your level of difficulty you are interested in. And of course, you have many courses. You can change the user interface as per your liking or per your requirement. You can track your progress. And of course, you can perform very powerful searches and also test yourself. So these are the videos which will help you. So now we move on to the last set of 5 Q&A, because the prior 15 have been covered in lecture 2A, 2B, and 2C. So we start with the topic of our interest, which is complexity analysis, and we go to the required set of questions, which were basically we are looking at the last set of questions, starting from question and answer number 16. So what is the role of data structures, array versus linked list in algorithms? Okay, with reference to the time complexity. So because the data structure has a very profound and critical impact on the overall computational complexity, time complexity, as well as the space complexity. And the choice has to be very done very carefully. So of course, we'll cover the time complexity and the space complexity with the perspective of the time complexity. Now, why I have selected array and the linked list, because they are the fundamental data structures, and their combinations and their applications can be used at different scenarios in different environments. All right, so let's look at the time complexity for the array to access. Now, the access time complexity is order 1, because any address location can be accessed randomly. Random means that it doesn't have to traverse it, and the time taken is order 1. So the linked list, if I say get me the sixth element or the seventh element or the eighth element, this is not searching. So I'm looking, so the program has to go to that location, move across the linked list. That takes order n time. So that is not very fast. Then is the search time complexity. Now, when we are performing the search, the array could be sorted and the array could be unsorted. So if the array is unsorted, then because random access provides me the content at a certain location, here I'm looking for something. So check the first location, second location, and end up checking all the locations, and maybe you don't find it, maybe it doesn't exist. So that takes order and time. And if the array is sorted, then it takes log of n time, because I first look at the approximate middle position, and if the item is not there, then I took a look at the right or the left, because it's sorted, and depending upon, basically I'm cutting down the search space, so that takes order log n time. In a linked list, if I'm searching, because in the linked list there is no concept of the ordering. Okay, one could implement some ordering, but it doesn't help, because one has to traverse the linked list all the way have to traverse it, so there's no point in wasting time ordering a linked list. So the time taken for a search on a linked list is order n time. So insertion and deletion time complexity, for an array, the time complexity for is it could be beginning. The worst case could be beginning or in the middle. So if something is inserted in the at the beginning of the array, one needs to move all the items all the way one position ahead. So that takes order and time. That's very slow. Or if it's the insertion is in the middle, the same thing. So half of the elements, which is order n, which is actually n by 2, have to be moved. And of course, if the insertion has to be taken place at the end, that takes order 1 time. All right. So we have looked at the access time complexity. We have looked at the search time complexity. Now let's look at the insertion and deletion. So that we covered most of it for the array. So for the linked list, the time complexity to insert at the beginning is order 1. Why? Because we have the linked list, and the insertion takes place using the pointer to the head of the linked list. So that takes order 1 time. And even if the insertion has to be taken place at the end, one could have pointed towards the end of the linked list. So that again takes order 1 time. The problem comes when we have the insertion at the end or the middle without the end pointer. So if the insertion has to be taken place at the end, one needs to traverse the entire linked list. So that is order and time. And if the insertion has to be done at the middle, then of course the complexity function is n by 2. So we ignore the constant, so the time taken is again order n. Memory allocation and the time complexity. So memory allocation, you create an array. You just data structure can drastically influence, of course. So when you create an array, so let's me okay. So the initial allocation takes order 1 time. Now, if the array needs to be grown, okay, then we have a disaster. Disaster in terms of the time complexity, because all the data in the array, that has to be reallocated. So that takes order and time. And if it's a linked list, then of course the time complexity of declaring a linked list or is order 1, and the linked list grows dynamically. So there is no issue of a reallocation. You just keep on adding towards the end of the linked list. So that's one of the benefits of linked list. So here's a summary of the time complexities which we looked at. So access by the index for the array is order 1. By the linked list, looking at the say the fifth position or the n by 2 position, is order n time. Searching unsorted is order n for an array, and linked list is order n because we have to go all the way. And if it's sorted, I'm sorry, this is for unsorted, and when it is sorted, it takes log of n time, and it is order n time for a linked list. So we see that time complexity. Okay, from a perspective of time complexity, you see that it is a clear winner in terms of time complexity using an array versus a linked list. Now, of course, if you recall, then we also discussed changing the size. So resizing the array takes order n time. So there is no such thing for a linked list. And if you are interested in reading more, here are the references. So you see that we have a rolling kind of a unique menu based approach. So what is the role of data structures, array versus a linked list with reference to the space complexity? Earlier we were looking at the time complexity. Now we look at the space complexity. So space complexity for the array is order n. So we declare the array, and we are looking at a one-dimensional array right now. So it has what is a one-dimensional array, and of course that can be a dynamic array, okay, which is in Java and vector in C++. So basically the size can be increased, right? And the space complexity is order n. The space, the memory used, but with potential overhead. And that overhead means it comes into consideration when the size of the array has to be increased. And there is no such issue with the linked list because the size increases dynamically. Space utilization, we will look at the space efficiency for the array, and we'll also look at the memory overhead for the array. Now for the space complexity of a linked list, the space complexity is order n. Order n. This is not the complexity function, this is the time, this is the space complexity. And the reason is because of the data element, and of course the pointer, which takes more space. So there is additional space of the pointer. For a single linked list, of course, if it's a doubly linked list, then the pointer space increases. So we'll go into all those details. And there is the memory overhead, and the space complexity is of course order n. Space utilization, memory efficiency, and there is no wasted space. Wasted space means that as opposed to an array in a linked list, what you have. But in an array, since it does not grows dynamically, unless of course it's a vector, we'll talk about it. So if we declare an array, so the space is set aside, and so there is wastage of space. So if we compare them, the linked list versus an array with reference to the space complexity, so we have this auxiliary memory, okay, memory which is used, and this could be recursion, stack, and function calls. Additional memory can also be being used. So the array size is fixed, that we have discussed, and the time in the array of n elements takes up contiguous blocks of memory. So the access time is fast, and the space complexity is order n. But remember that there is a wastage of space, and when the space is insufficient and need to increase the space, the new array of double size needs to be created, and creating that double size means that one has to reallocate, and that takes time, order n time. And of course that with the space complexity order n, there is still the unused space that I will already mention to you. So example could be doubling the size of the array, and periods of wasted memory are there even when we double it. And of course, then still we have order n additional space which is unused till it becomes used. So when the size requirement becomes more than what was declared. So we have that order n space complexity for the array, and then additional order n time complexity for reallocation when the space size is insufficient. So space utilization only store the data elements themselves. In the array, there is nothing additional stored. and there are no pointers and there is no management of pointers. But as opposed to array in a linked list, the resizing is dynamic. It is dynamic and it happens dynamically. There is no reallocation, there is no declaration of additional space. Okay, so they do not exactly match the required size. So there's no declaration and the size increases dynamically as more pointers are added. Okay, so for a singly linked list, the space complexity is order n. It is the data element and we have the pointer element. Okay, but the constant factor is larger than of an array. What is that constant factor? That constant factor is at least 2, which is the space of occupied by the data itself and the space required by the needed by the pointer. So typically the spaces are mentioned over and you can read them. So if it's a doubly linked list, then you have to store 2 pointers. You have to store 2 pointers. So you know that the constant factor is further increasing. So so you have pointed to the next node and you pointed to the previous node. Of course, this helps in certain operations. This results in a reduction in time complexity of certain operations. Then is the space utilization, memory efficiency, less memory efficient compared to arrays. Linked list is less memory efficient as compared to array because of those pointers, and no wasted space. Do not require extra memory for resizing. You just keep on adding and adding, and just keeps on increasing. Memory is allocated dynamically. In the array, there is no dynamic memory allocation. So let me. This is the summary of what we have discussed, and to have a concrete understanding, actually, in let me look at discuss this example with you. So we have this graph over here, and this graph consists of 5 nodes. You can count the number of edges. So this is the array representation. So we have 5 vertices. So the declaration consists of 25. So the space complexity is order n square because this is a two-dimensional array, right? So 5 means 25, order n square. Now this is the adjacency matrix representation, and we have we have a array of pointers. And if you see that we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So we have 14 nodes. Okay, we have 14 nodes. Why? Because there are 7 edges. We have 14 nodes and 14 into 2. 14 into 2, you can see that that's 25. Why I am multiplying by 2? Because of these pointers. Now, if there were fewer edges in this graph, fewer edges, this space complexity would be the same, n square, but this would be highly efficient. It would not be 28. If there were, say for example, there were 4 edges. There were 4 edges, so this will be 25 n square, and this will be 5 plus 8, 13. That's it. So almost half of this amount. So we see that there's a benefit of having having an array, or benefit of having a linked list. Now the question is that which one is better? So the better, of course, depends upon the application, and then we need to discuss the trade-off. So that's the next question and answer. What are the trade-offs between time and space complexity for optimization in real-world applications? Let's look at it. Look at the trade-off between this time and space complexity, and continue with the real-life problems or the real-world problems. So we compare the in-place algorithms versus the algorithms that use extra space. For example, the merge sort requires extra space, which is order n, and as opposed to quicksort, which does not require extra space. The extra space is like order 1, which is not related to the size of the input. So what is the impact of that extra space, and what is the trade-off? We will look at it. And then is the pre-computation versus real-time computation. So if the results are pre-computed and they are stored, of course that would require memory. So how would it reflect upon the computation time? And what is the trade-off? And then is the approximation algorithms. Approximation algorithms basically give a proof of the bound about the quality of the solution. So for example, consider the vertex cover problem. So the approximation algorithms, they give a guarantee that the solution provided is not going to be twice as compared to the optimum solution, not more than twice. And it is using a greedy approach. So basically, this is a trade-off, because the trade-off is we are not exploring all the possible solutions. As a matter of fact, it's also not possible. It's very expensive, which we will cover in the theory of NP completeness. So let's look at the in-place algorithms. Use only a constant amount of additional memory. Of course, there are some variables, and there can be which are used in performing the algorithmic task. But that is order 1. So maybe 5 or 6 variables, maybe 10 variables at most, and which is independent of the total size of the input. So like a quick sort and heap sort perform more operations than their non-place counterparts, non-in place. Why? Because quick sort and heap, they basically are they are in place, okay? May require more steps to rearrange data. Why more steps? Because the space is limited and have to work within that limited space. So the constraints are on the memory usage, but can be harder to implement and debug because the resources are limited. That increases the complexity of the problem itself. So the algorithm which work with extra space solution are easier and solutions are fast also, right? Because there is no kind of moving around, for example, over the stack. So they consume more memory, which can be a problem in memory constrained environments. So merge sort is a classic example of non-in place merge sort, which takes order and time, right? And since it takes order and time, so it is like, for example, comparatively easy to code and maintain. But whereas the quick sort, which is in place, requires order and log and space for the recursive calls for placing those recursions on the stack, right? So you can see that what is the effect of the time and the space and the trade-off. Pre-computing versus real time. So pre-computing certain values and using them in the subsequent values, okay, that of course a cost, there's a cost of the space, but that reduces the number of calculations because what has been computed, it is used subsequently. So reduces the cost of calculation, the cost of computation, and the real-time computation performing during runtime avoids the pre-computation. So if it's done in real time, then there is no pre-computation. And when there is no pre-computation, there is no space required to save it. Okay. But the trade-off using extra memory but leads to higher time complexity because of the repetitive computations. Of course, if there was space being used to store the partial results or store the results and use subsequently, that was of course requires space. But if the space is not used, is not available, then there is a lot of repetition. So, for example, in route planning, GPS systems. So these are some of the examples. Then are the approximation algorithms. These algorithms, which I've already mentioned, belong to the class of NP-hard problems, and they run faster because they do not explore all the possible solutions. Why? Because the possible solutions are non-polynomial and they cannot be explored. So when they cannot be explored, so this will take definitely less time. Okay, and these algorithms may use more space by storing the heuristic results and then using them subsequently. So the prime example is the vertex cover problem. So now we end this subtopic with how to verify the correctness of an algorithm. So you have an algorithm and people discuss with me that they have a solution. So how they would know that the solution is actually correct? So there are a number of standard ways of looking at the correctness of a solution. And for example, one is the formal proof of correctness. So mathematically demonstrating that the algorithm actually does work. Okay. And it will and if it has to work, it should meet the requirements that it should eventually finish, it should eventually terminate, especially for recursive solutions. Because if they are not properly developed, if they are not proper base cases, which we will discuss in the topic number 3 on recursion. And partial correctness give the correct result if it terminates. Basically, while it is working, those partial results are also correct. And total correctness, and it always terminates. And when it terminates, it does have the correct solution. And of course, there are a number of ways of doing it formally. One is the inductive reasoning. So we prove the base case, then we prove a case where it works, and then we prove that it works for all the larger cases also. So that is the inductive approach. Then is the test case and unit testing approach. So testing the smallest parts of the algorithm. There are certain tools available. There are certain frameworks available, which you can see on the screen, and look at the boundary cases, empty inputs, special cases, and see how the algorithm handles those conditions, and then also try the random inputs also. So basically, it's not just testing one case and comparing the output of the algorithm against expected results. So if these things work out, then there's a certain level of confidence. Okay. Now there is no guarantee that this will work for all the cases, but this is a good effort. Correctness by exhaustive testing. Now this is a brute force approach, and this is computationally expensive also. So you manually compute all the possible scenarios, okay, and then you apply those scenarios, or you use some code to generate those scenarios and apply all of those scenarios. Of course, this is very exhaustive, and of course, it's very expensive, but that is one way. Comparison with a known correct algorithm. Compare the results of your algorithm with the results of a known algorithm. So there are certain standard algorithms for sorting, standard algorithms for searching, for clustering, for classification, for there's a long list. So you basically select certain data sets and apply the standard algorithms on it, and then you apply your algorithm on that the same data set and compare the results. Run your algorithm on the correct algorithm. If they match, suggest your algorithm is likely correct. There's no proof, and useful in implementing more efficient versions of existing algorithms. So the algorithm is the same, but you have a better approach, you have a better solution. For example, you can compare it with the merge sort and quick sort and so on. Performance and complexity analysis. Now, complexity analysis, the space complexity and the time do not directly relate to the correctness. Okay, but it ensures that the algorithm can produce results of in polynomial time using polynomial space. Peer review. So you have your algorithm reviewed by its correctness by the peers. So there are a number of ways of doing it. For example, within your organization, or say, for example, you submit a paper to a journal or to a conference, or submit a patent. So the time varies. So that could vary from one month, maybe weeks to months, and so on. And of course, there's a proof of termination, especially for recursive algorithms that we will discuss in the recursion, and which involve the loops. Code review and static analysis. So static analysis tools can be used, or doing a manual code review, and tools like linters and static analyzers can be used to evaluate the code. There are no unreachable code parts, and there are no other bugs and so on, because certain bugs are difficult to catch as compared to other bugs. And verifying the correctness of the code, for example, sorting is performed, and you can see that every one iteration a number reaches or placed at the correct position. So that is a good proof. And largest to unsorted elements. So that's one way of doing it. So we see that there are certain ways of proving the correctness of an algorithm, and certain they have their strengths and they have their limitations. So that is all. And now we will, in the next video, move on to the section topic 3, which is recursion. Thank you very much.